Hey there. Okay, so we're going to move on to this example, which talks about a rodent population in a particular region. And based on how many predators there are, the rodent population could increase or decrease, and it's going to fluctuate. So when there's lots of predators, they get eaten. So there's less of them. And when there's not a lot of predators, they're not getting eaten. So if we use the variables are, RFT is going to be the population of the rodents in any given year, and T is going to be the number of years that have passed since 1976. We need a frame of reference. So the frame of reference for this example is 1976 would be the beginning, let's call it. Now, the best part about this question, unlike the Ferris wheel question we did earlier, was that we've already got the equation given to us. So we should be able to identify a lot of things just from the equation in terms of this population of rodents. So I hope you took a second and just asked yourself, what information can I tell about the population just from this equation? Now, I know the format of the question is a little different than what we're used to. The equation usually, when we're given an equation, has the a first and then the function, and then we have a k bracket x minus p plus q. So that's the general form. So this one's got a slight variation. This particular one has the q coming first. Here's your a, and then 30 is your K. And so we do have, and we actually don't have a P, which is lucky for us, there's no phase shift. So recognize that it has been rearranged, but the parameters still apply. So based on this equation, the 2500 is your Q. And what did Q always represent? That represented our average number of rodents. Then the 1500 is your A. It's in place of the A, which is your amplitude. So what can we tell about the rodent population just by knowing these two parameters, the average and the A? So remember, think about your dotted line, your average line. There's your average of your rodent population, and the amplitude is 1500. So I'm hoping that you're recognizing that you can identify the max and the min just from knowing the average was 2500. So if 2500 is the average and the amplitude goes up to the max, so this amplitude is 1500, and then coming down, the amplitude is also 1500, then we should be able to do a quick calculation to determine that the maximum is going to be 2500 plus 1500, or in other words, 4000 rodents is the most populations we can expect. So we've calculated the max very quickly. We can also look down below the average and calculate the minimum number of rodents we'll ever expect, 2500 minus 1500. So you're subtracting Q minus A this time. So 2500 subtract, and that gives us 1000. So right away, just by looking at the equation and doing a little simple math, we can deduce that there's never going to be less than 1000 rodents, and there'll never be more than 4000 rodents. And the average number of rodents we'll see on any given year is 2500. So that's just by looking at the equation. There's another parameter in the equation, the 30. That's in place of my K. And what did the K always signify? So remember, K was related to the period. So if K is 30, and we know that the period is equal to 360 divided by K, then what can we deduce about the period? And what does that actually mean about the rodent population? So 360 divided by 30 is 360 divided by 30, 12. Sorry, I was writing 12. So what does 12 mean in terms of the rodent population? So remember up here how we defined T. T was defined to be the number of years since 1976. So by getting a period of 12, that's implying to be years And so what's happening is the rodent population is fluctuating between 1,000 and 4,000 rodents every 12 years. Okay, that's every 12 years we're going to go back down or go back up or whatever order we're going in. So that's all information we can get just by looking at the equation. So let's draw a sketch. We kind of already did, actually, if you thought about what I was drawing over here. This is kind of a quick, rough sketch, but now let's put it to scale. So what we needed for our horizontal scale, remember our horizontal scale was taking my period, which you now know is 12 years, and I always suggested getting the quarter period. So a quarter of 12 years is 3 years. So I want my scale to go at least every 3 years. I want to show every 3 years. And then my vertical scale, I need to have 2,500 in it, and I want to have a minimum of 1,000 and a maximum of 4,000. So I've come over here and I've made increments of 1,000 going up vertically and to 24 because they actually asked me for 1976 to 2000, which is a period of 24 years. So I've got 24 years in here. Now, I want to make sure you understand, though, even though we calculated 3 years to be my quarter period, they're nice increment blocks. So I went up by ones. Okay, so let's go through the same process of graphing where I like to put my average line, which we knew was 2,500. That's my little imaginary line. And then I like the step pattern. So I'm going to start at 1976 and I'm just going to plot points that are every quarter period, so every 3 years, starting at, actually, where did they say it starts? Because the equation was given to us and it was a positive sign equation, then we can assume the shape is going to start at the average, and then we can, so we're going to assume it's starting at the average and going up from there because the equation indicated that. So I'm going to start at 2,500 rodents, and every 3 blocks to the right, so every 3 years, I'm going to go up to the average, up to the maximum first. Then another 3 years later, so now I'm at 6 years, I'm going to come back down to my average. 3 years later, at 9 years, I'm going to go down to my minimum. 3 years later, I'm going to go back up to my average. So one full cycle after 12 years, with a nice smooth curve has been graphed, but they want to go till 2000. So I'm just going to follow that step pattern until I've got 24 years. So over 3 down to average, over 3 down to minimum, and over 3 up to average. Okay, and then connect your nice smooth drives. So there's my graph. And now we should be able to answer some questions based on the rodent population. So how many rodents would we predict in the year 2013? So let's go back to the graph for a second. In 2013, so that is what, 37 years after 1976. So we don't have that on my graph. But remember, every 12 years, we started back at the average. So 12 years, 24 years, 37 years is going to be somewhere over here. And it's going to be exactly 1 year more than 36, because 36 would have been my next full cycle. Agreed? Every 12 years was one full cycle. So 36 is going to get me back to this average point remember, every 12 years. So the next circle, I don't have room on my graph, but somewhere over here at 36 is going to be where I hit the average. So at 37, where is it going to go? A little bit more than that. So somewhere up here. So I might predict something in the range of 3,000-ish. That's a good prediction for where I would expect it to be in the year 2013. Now that's using the graph. Using the equation, if I know it's been 37 years after 1976, I can take my equation and I can substitute in for t 37 years, and that's a quick calculation. So let's do that right now. I'm just going to pause it and I'll meet you back after you do a quick calculation to figure out exactly how many using the equation. Okay, so if you followed your BEDMAS rules, and be really careful, follow BEDMAS, you should not have added 2,500 plus 1,500 first. First, you should have multiplied the 30 by 37, then taken the sine of it, then multiplied that answer by 1,500, and then worked backwards and added to 2,500. So if you followed BEDMAS correctly, you should have got 3,250 rodents, which makes sense because based on my prediction, I knew it was going to be just over 2,500. I predicted probably, and actually, let's look, looking at this graph again, one second. If I went exactly 1 year after the average, then we should actually be, if I look at what part of the graph I do have, that's about right there, right? 1 year after the average. So if I went to 12 years, 1 year after the average, looks like it's about here. So as a prediction, I might have been able to say 26 would have been about here, sorry, 26.5 would have been about here. So it does look like it's about 3,200 now that I think about it, okay? So 3,200 would have been a good prediction based on the graph and as well validated through the equation. So that's the easier calculation. Just like the Ferris wheel question, what if we were asked to solve for the time when the population was given? So this is the one where you are setting 1,300 into as your R, you're solving for the T. So by replacing R of T with 1,300, now our goal here is to solve for this T. And just like in the other question, it's embedded inside a bracket, so I've got to follow my BEDMAS rules, or SAM-DEB rules, sorry, and do reverse operations to BEDMAS. So by quickly just subtracting both sides, 2,500 from both sides, and then dividing by 1,500, I should end up getting negative 0.8. I'm skipping a couple of steps here, but I'm just following, I'm getting rid of this 2,500 first, and then I'm getting rid of this 1,500. So I get negative 0.8, and that's equal to sine of 30t. Now I'm really hoping you remembered my strong encouragement, my hint, my suggestion that when I'm about to inverse sine this ratio, I do not want to use the negative in my calculation. As I told you in the other video, I would prefer you to find this angle here, the related acute angle, by using the positive ratio. And then based on the fact that it's the sine that you're looking for, I'm going to use CAST rules, C-A-S-T, and knowing CAST rule knowing the sign is negative in this T quadrant and this C quadrant, I can use 180 plus whatever that theta A is, and 360 minus whatever that theta A is. I would strongly encourage you to do that because, again, if you don't and you plug in negative 0.8 and inverse sine that, it's going to give you this answer. Okay, what your calculator is trained to do is to go to the closest answer that would have produced a negative ratio. And so for your calculator, it would have come down to the C quadrant. So yes, you will get this answer, but how then are you supposed to get the answer in the T quadrant without making a careless error? And I can tell you right now, a lot of people make very careless errors trying to figure out the second angle, even though they found the first one easily by plugging the negative in the calculator. So to avoid that, just trust me, pretend the negative is not there, split this into two parts, and take the inverse sine of positive 0.8. Okay. Okay, so if you found the inverse sine of positive 0.8, you would have got 53.13. That is your related acute angle. That's the one in this quadrant, but we want the one in the T and the C quadrant. So I'm going to break my question up into two parts. I'm going to do a quadrant 3 part, and I'm going to do a quadrant 4 part, and I'm going to say, I'm going to say 30t is going to be equal to 180 plus whatever the inverse sine of 0.8 was, which I'm just going to write it as 53.13 because I just found it. You could have found it within this solution as well. sometimes I show that. Sometimes I show that way where I actually do this sine inverse calculation within here. But it's up to you. If you want to do it on the side and then bring it into the solution, you can do that as well. So this one's going to be 360 minus that theta A, which we just calculated to be 53.13. And now it's just a matter of simple calculation to solve for t. I'm going to let you do that. Okay, so you should have got these two answers. The rodent population will hit 1,300 rodents after 7.8 years and 10.2 years. Now those are only within one revolution, right? That's only within one cycle. Let's actually jump back to the equation, the graph, sorry, and confirm 7.8 and 10.2 for 1,300. So 1,300 is down here. I'm just going to draw this blue. So 1,300 is about here. So if I come across all of the points where that blue line crossed the axis would be the answers that I'm looking for. So I'm going to just put some happy faces in here. We got 7.8 and 10.2. So that right there looks like about 7.8, so that's confirmed. 10.2 looks like about there, that's confirmed. So those are the only two answers that my calculator gave me. But remember, this is periodic, which means the rodent population is going to hit 1,300 again over here, and again over here, and it's going to continue that pattern. So every 12 years from each one of those happy faces, it's going to repeat itself. And so what we want to say, because this question didn't ask us for the first two times it hits 1,300, it asks us when the rodent population hits 1,300. So this is an extra little important step that you have to answer if the question does not give you a domain or does not ask you for a certain number of times. If it just says when will it reach 1,300, you actually have to add this extra little statement, and it basically says take the 7.8, so that's happy face number one, and add a period of 12 years infinitely forever. So I'm going to use a variable n to imply infinitely forever. And then I'm going to do the same thing and say, well, at the second happy face, which was 10.2 years, every 12 years after that, it's also going to hit 1,300. So I'm going to say 12n here. And what is this n? N is just saying any number of times that it can happen, and it's happening infinitely. So I have to say where n is an element of all integers. So when n is 0, then that's 7.8 years and 10.2 years. If n was 1, well, then that would be, if I just come back to the graph, if n was 1, what's 12 years after 7.8 years? 19.8 years. So that's this happy face right here, 19.8. If n was 2, what's another 12 years after 19.8? That's not on my screen, but it'll be somewhere over here, and that'll be 31.8. So increments of 12 years from this first happy face is your first solution, and increments of 12 years from the second happy face is your next. So your final therefore statement for a question like this would basically be saying, therefore, the rodent population reaches 1,300 every 7.8 plus 12n years, or I should say, and 10.2 plus 12n years, where n is an element of all integers. Okay, so that's sort of your therefore statement, and this is sort of the new learning. So right here and right here is what I really need you to make sure you say if I don't give you a domain. Okay, so I hope that helps answer the rodent property question, and I think you're good with modeling periodic functions with word problems.